Hello everyone. Today we are going to learn about DFT and IDFT, which stands about discrete Fourier transform and inverse discrete Fourier transform. Now the prerequisite for this is knowledge about CTFT and DTFT. Coming to transforms first, what is basically a transform? A transform, it converts a signal in one domain to another domain. So we had learned about CTFT, where a continuous time signal x of t gets converted into a continuous signal x of omega in the frequency domain. DTFT, which stands for discrete time Fourier transform, here the input signal in time domain is discretized. So x of t is getting converted to x of n, and now when it is applied to DTFT, it gets converted into x of omega, which is still in continuous frequency domain. Now, even though the input is discrete, for usage in computers, x of omega has to be discretized. So we need a new kind of transform where x of omega gets discretized into x of k. So that leads to the usage of DFT, where x of n, that is a discrete time signal, is getting converted into x of k, which is available in the discrete version in the frequency domain. How do we discretize a continuous function? Now, x of omega, as we know, is continuous and periodic over the period 2 pi. If we are generating n samples of this continuous signal in that space of 2 pi, then each sample would be spaced apart by 2 pi by n, which gives the time gap, or the gap between two consecutive signals in this frequency domain. Repeat, not time gap, but gap between the signals or the samples in the frequency domain. And to represent each sample, we use a variable k, just like we use x of n, where x of n is x of t at t equal to n capital T, where small n is a variable that represents sample, and capital T is an interval between two samples. Thus, each sample of the decimated x of omega can be represented as k into 2 pi by n. If you look at the formula for CTFT, we know that x of omega is equal to summation n equal to 0 to n minus 1 x of n e raised to minus j 2 pi, e raised to minus j omega n. Now, whereby we can understand that this is a continuous signal and continuous in the domain omega, even though the input signal is discretized. Now, when you look at this DFT and the formula here, you can see that x of k is equal to summation n equal to 0 to n minus 1 x of n e raised to minus j 2 pi nk by capital N, and instead of x of omega, you're getting the discretized version of x of omega as x of k. Now, inverse discrete Fourier transform has to be used to get back x of n from x of k. Now, if you look over here, the formula is going like this: x of n is equal to 1 by n summation k equal to 0 to n minus 1. Mind you, it is k which is equal to 0 to n minus 1, because we are using x of k as the input. Now, x of k e raised to j 2 pi nk by capital. Now we are looking at a numerical right now, where we are trying to evaluate a 4-point DFT of the given sequence x of n is equal to cos n pi by 4. Now, it is already mentioned that it is a 4-point DFT, so which means your capital N should be equal to 4. Now, you need the samples to be very specific, so x of n can be treated as a 4-input signal, and we have cos of 0. By substituting small n from 0 to 3, you get cos 0, cos pi by 4, which is cos 1 into pi by 4, which is cos 2 into pi by 4, which is pi by 2, and cos 3 pi by 4, which are the inputs. So it can be obtained as 1.7070 and minus 0.707 as the input. Now, applying the formula, we can get the output of each x of k, where the value of k will be from 0 to 3. So we have to find out x of 0 for k equal to 0, x of 0 for k equal to 1, x of 1. It's plain substitution, where you have to consider all values of n from 0 to 3 and a fixed value of k for each output that you're finding, and you get the results as follows: 1 minus j 1.414, 1 and 1 plus j 1.414, and now you have the final result of the DFT. Just like that, you can find out the inverse DFT of x of k for another numerical 1, 2, 3, 4. The formula here is the one that was explained before. X of n is equal to 1 by n, summation k equal to 0 to n minus 1, x of k e raised to j 2 pi n k by capital N. If you look at the difference, you can see that here the formula is e raised to minus j 2 pi n k, and here it becomes e raised to j 2 pi n k. So solving for that, you again have all these formulas, the same formula that you can use here. Now here the output has to be found in terms of n, and n is again 4, and we consider the values of n as 0, 1, 2 and 3, which is fixed, and now the summation is ranging from 0 to 3, and in the as an overall parameter we have 1 by n, which is equivalent to 4, as n is equal to 4, and you solve always these things by substituting the values, and you get the following values as the final solution. So we have 5 by 2, minus 1 by 2, minus j 1 by 2, minus 1 by 2, and minus 1 by 2 plus j 1 by 2, and this is a final solution of the inverse DFT of x of k equal to 1, 2, 3, 4. As an assignment problem, you can do the following questions. Find the endpoint DFT of x of n equal to a raised to n for 0 less than or equal to a less than or equal to 1, and determine the IDFT of x of k equal to 3, 2 plus j, 1 and 2 minus j. Thank you, and I hope the topics were clear. In case of any doubts, please get back to us, and in the meanwhile, if you need any reference, you can look into the following books. Thank you and have a great learning.